A wise old man once told me to use stats wisely. Actually, we're talking today about using stats wisely, specifically with studies and experiments. So we've learned all about how to do surveying, all about how to do experimenting. Today we're going to talk about drawing conclusions and when we can do that and when we can't. So a couple different things we're going to talk about with that. Let's start off with this example. How much do National Football League players weigh on average? In a random sample of 50 NFL players, the average weight is 244.4 pounds. Question: do you think that 244.4 pounds is the true answer, or true average weight of NFL players? Explain your answer. Well, my guess is it's probably not. But the thing is, we're never going to be perfectly correct on a sample anyway. Problem here is, though, that there's different samples of 50, and they might have different weights. So it would be surprising if the estimate was equal to the true average of NFL players. But this also causes some variability in our sample. And that is actually called sampling variability. It has a term for it. So sampling variability refers to the fact that different random samples of the same size from the same population produce different estimates. You're just getting 50 different random people, so it's hard to get an exact same number. That is called sampling variability, and it's to be expected. There's always going to be some sampling variability. Now, would you think it would be more likely to get an estimate close to the true average? Which one would be a better estimate, having 50 players or a random sample of 100 players? Hopefully you're thinking 100. And that's part of our key principles of experiments. We want to have replication. We want to have a lot of data. So a random sample of 100, because estimates tend to be closer to the truth when you have a larger sample size. Okay? And from a visual, larger sample sizes do tend to produce estimates that are closer to the true population. In other words, larger samples, more precise. Larger samples, more precise. All right? Now, well-designed experiments allow for inferencing. And when we say inferencing, we mean, can you draw conclusions? And our cause and effect is something that we've talked about. We're going to talk about that more today. So in an experiment, there are two ways to explain why the average responses for one group is different than the average responses for another. So like your results from your treatment. It's either going to be the treatment actually does not have a different effect for the different groups, and it's just by chance. That's option one, chance. Or option two is the treatment actually causes a difference in the average responses of the groups. Now, this is assuming everything else is done well in our experiment. So we want to look at that chance idea a little bit. So, situation. Mr. Wilcox and his students decided to perform an experiment looking at caffeine intake. I know a lot of people like to take caffeine in various ways. And pulse rate. So they're in an experiment. 10 student volunteers were randomly assigned to drink cola with caffeine, and the remaining 10 were assigned to drink caffeine-free cola. Okay? Now the table below and the graph show the change in pulse rate for each student. Final pulse rate minus the initial pulse rate. So how much it changed. Okay, so if you look at this 0 line, that's like no change. This many people had an increase. Only 3 had a decrease. And you can see that over here as well. And those 3 happen to be in the no caffeine. Everybody in the caffeine had an increase or stayed the same. So if we take those averages, it was 3.2, the mean change was 3.2 in the pulse rate for caffeine and only 2 in no caffeine, which is still actually a bit of a change. But the difference is 1.2. So that may or may not be significant. We want to decide if that's actually a significant change. So the dot plots provide some evidence that caffeine does have an effect on pulse rates, but is it significant or not? This term statistically significant is something we want to look at. Now, the purpose of random assignment to roughly equally groups gives us that opportunity to say cause and effect, to say that caffeine actually would cause increase in pulse rate, because some people have different metabolism and they just metabolize their caffeine differently, so it should be roughly equal between the two groups. So that's a good thing. But how do we tell if that mean change of 1.2 is actually significant? It's either got to be by chance or it's got to be because of the caffeine. Again, there are two options here. So what we're going to do is we're going to look at whether that's a significant thing or not, and we're going to look at a trial, a simulation. So we're going to run a simulation of 100 trials of this, as if the caffeine does not impact the pulse rate. Okay, using technology, we can run these trials, and we did. And here's the data. So on average, the change in pulse rate, caffeine minus no caffeine, was listed here. We don't have the actual average, but these are all the different possible results. So caffeine average minus no caffeine average in mean pulse rate gives you all this data. It's fairly normal. Surprisingly, not a ton at the 0. But we want to look at this to see if 1.2 is unusual or not. And where does 1.2 fall? If you look at how it's divided up, it kind of falls right in here. So is that in an unusual, is that significant? To do that, we got to use our 5% rule. That's going to be one way to do it. We can be given different values for what would actually be statistically significant, but we're going to say that 5% rule. If it's less than 5% of the population falls in that range, like on the higher or lower end, so we're going to look at all of this, then it would be considered significant. However, if you look at this, that's a total of, what do we have? Got it on this next one, 19 times. So the idea of statistically significant, when the observed results of a study are too unusual to be explained by chance alone, we can say they're statistically significant. And a rule of thumb is that 5% rule, just like we've talked about in the past. So with that 5% rule, if I'm looking at this, this is 19 out of 100. That's actually 19%. That is not significant. Okay, it's not within the upper or lower 5%, so I can't say that that's significant. But that's the idea. We want it to be so rare that it just wouldn't happen by chance. This seems like it could happen by chance. I've got one other example to look at for this. It says, is talking on a cell phone while driving more distracting than talking to a passenger? Because people talk. So David Strayer and his colleagues at the University of Utah designed an experiment to help answer this question. They used 48 undergraduate students as subjects. The researchers randomly assigned half of the subjects to drive in a simulator while talking on a cell phone, and the other half to drive in the simulator while talking to a passenger. One response variable was whether or not the driver stopped at a rest area that was specified by researchers before the simulation started. So how many of them actually stopped and noticed it? Here's the results. 33 of them stopped at a rest area. 15 of them didn't. And you can see the breakdown by whether they were on a cell phone talking to someone or talking to a passenger. So we want to calculate the difference, passenger minus cell phone, in the proportion of students who stopped at the rest area in the two groups. So of those who stopped, because it was the same who were talking to a passenger and who were doing a cell phone, of those who stopped, 21 out of the 33 were talking to passengers. And we want to subtract that from that we want to subtract the 12 out of 33, which is those who were on a cell phone. That gives us 9. Oops, sorry, we actually do care about whether they stopped or not. So I'm going to say 20 of the passengers, the ones who are talking to passengers, out of the 24, 21 of them stopped. Out of the 24 who were on the cell phone, 12 out of them stopped. Okay? So if we subtract those, that gets us 9 out of 24, which if you do the math, that's about 0.375. Okay, that's the difference. We want to know if that's significant or not. If it was like that much more stopped who had a passenger than a cell phone, to see if it's really more distracting for the cell phone. Well, how to do that, not something you have to know how to do right now, but how you can do that is you can use technology to actually simulate this. And by chance, these are all the data points we have. So let's look at 2 things from here. First question, there are 3 dots at 0.29, so that's right here. What do those dots mean in this context? Okay, so that is the difference. Again, we're looking at passenger minus cell phone, the difference in the proportion of people who stopped when they're talking to a passenger versus talking on a cell phone. So when we assume that the type of distraction doesn't matter, there was 3 simulated assignments that where the difference in the proportion of students who stopped at the rest stop was 0.29. That was the difference. Now, if you look at this, we want to know, is our 0.38 or 375 actually significant? Well, where does that locate on here? It's over in no man's land. There's nothing over here. So absolutely, it's higher than all of them, which does tell me that it is statistically significant. And because it is, we can make cause and effect conclusion that talking on a cell phone is more distracting than talking with a passenger, at least for subjects like these in the experiment. All right? So that is the first thing. We want to talk about statistically significant and be able to make conclusions that way. Now, the second thing I want to just talk about briefly is scope of inference. So I've got it's researchers who conduct statistical studies often want to draw conclusions. That's called inferencing, that go beyond the data. So here are 2 examples. The U.S. Census Bureau carries out a monthly current population survey, about 60,000 households. Their goal is to use data from these randomly selected households to estimate the percent of unemployed individuals. So that's how we get our unemployment percent. The question is, can we generalize to the population? And is there any cause and effect here? Something like cause and effect. Second one, scientists performed an experiment that randomly assigned 21 volunteer subjects to one of 2 treatments, sleep deprivation for 1 night or unrestricted sleep. The experimenters hope to show that sleep deprivation causes a decrease in performance 2 days later. What type of inference can be made from a particular study and these particular studies? But the answer totally depends on how it's designed. So let's do a recap of something we've already learned. What allows us to make inferences to the population, meaning generalizing? That has to do with a random sample. If we have a random sample, we can generalize to the population, which is something that oftentimes we want to be able to do. What allows us to make inferences about cause and effect? That's where it has to actually be a well-designed experiment. We'll say experiment with random assignment. You need that random assignment. That means we can have cause and effect. So one thing actually, we can say that one thing, our treatments actually cause the results. So to continue with that, typically well-designed experiments randomly assign individuals to treatment groups. However, most experiments don't take from a random sample from a larger population. It's just not convenient. So they'll take volunteers. So that limits these experiments to just saying cause and effect to the group that we have, not to the general population. Whereas observational studies don't randomly assign to groups, so we can't say cause and effect. However, they oftentimes use random sampling that can inference about the population. So there's pros and cons to both. If you can get both, it's even better. But if I go back to these examples, the U.S. Census Bureau, this is not an experiment, but this is a random sample. So random sample generalizes, but no random assignment. Okay? But we can generalize to the population. We can actually say that for the U.S. population, there's this certain unemployment because we can generalize to the population. Scientists perform an experiment. This is actually an experiment. This one has random assignment, but there's no random sample because it says we are taking volunteers. So no random sample, but yes, random assignment. So we can say cause and effect. So all we'd be able to say for this one is for volunteers like these, sleep deprivation causes decrease in performance. Okay? We can say the cause and effect, but we can't say like it's generalizing to a greater population, unfortunately. So I want to bring back this. This might help. If you want to make a chart out of this, where individuals randomly assigned or randomly selected. So random assignment versus random sample. If it's yes to both, we can inference about the population and cause and effect. If it's no to both, we can't do either. And then there's a little bit of both. So this is just a little two-way table talking about what I just said. And if you want to pause and write this down, feel free. But I'm going to jump to one last example. This is my example that we're going to jump to here. It says researchers at the University of North Carolina were concerned about the increasing dropout rate in the state's high schools, especially for low-income students. Surveys of recent dropouts revealed that many of these students had started to lose interest during middle school. They said they saw little connection between what they were studying in school and their future plans. So to change this perception, researchers developed a program called Career Start. The central idea of the program is that teachers show students how the topics they're learning about can be applied to specific careers. So to test the effectiveness of this Career Start, the researchers recruited 14 middle schools in Forsyth County to participate in the experiment. 7 of the schools, determined at random, used Career Start along with the district's standard curriculum. The other 7 schools just followed the standard curriculum. Researchers followed both groups of students for several years, collecting data on students' attendance, behavior, standardized test scores, level of engagement, and whether or not they were graduating from high school. The results showed that students at schools that used Career Start generally had significantly better attendance, fewer discipline problems, earned higher test scores, reported greater engagement in their classes, and were more likely to graduate. So what conclusion can we draw from this study? Explain your reasoning. You need to look for both things. Was there a random sample? And was there a random assignment? So was there a random sample? It says they recruited 14 middle schools. They did not randomly select from all middle schools, which means no. So we cannot generalize. Is there a random assignment? Well, it says right here, the 7 out of the schools determined at random. Yes. So, while we can't generalize the population, we could say for schools like these, can't say for all middle schools, Career Start increased all these things. They did what it was supposed to be doing. They increased levels of engagement, etc. So we can say that it caused that impact, but we cannot say for all schools, right? And that's the cause and effect idea here. So all this has to do with making conclusions and doing it in a way that's allowed and acceptable and wise. So we want to be able to understand the difference between random samples and random assignment. We also would like to look at the difference between statistically significant or not. That's lesson 4.3, using studies wisely. We'll see you next time.